This resolution was proposed by Rolf Landauer in 1960, nearly 100 years after Maxwell proposed the conundrum. Landauer's principle states that any logically irreversible manipulation of information, such as the erasure of a bit or the merging of two computation paths, must be accompanied by a corresponding entropy increase. And this has come to be seen as a fundamental limit to the efficiency of computation. Both Maxwell's conundrum and Landauer's resolution are fascinating because they highlight the fundamental link between entropy and information. Firstly, they show that information about a system allows us to extract useful work. If you have perfect knowledge of the state of all particles in the box, you could open and close the door in exactly the right sequence to sort the particles any way you liked. You could turn any perfectly known equilibrium state into literally any other non-equilibrium state. You could turn information into work or into structure. But ultimately, possessing that information does increase entropy. You generate heat as you compute, in particular as you reset your own memory. The entropy of the universe must increase, and yet knowing the microstate of a system, no matter how thermodynamically mixed, allows you to decrease its entropy. As long as you can power your computation, information is power. Claude Shannon, the father of information theory, was deeply inspired by the close connection between entropy and information. He defined a new type of entropy, Shannon entropy. It can be interpreted as the amount of previously hidden information that can potentially be revealed by the observation of a random event. In a sense, it's a measure of the uncertainty of the event. The more uncertain or more unusual an event, the more revealing it is than a more predictable event. So for example, the roll of a die has more entropy than the flip of a coin. There are more potential outcomes in the former, so more uncertainty has been eliminated when the die is cast. Shannon used the term entropy for this measure because his formula was almost identical to the formula for thermodynamic entropy. Just multiply by the Boltzmann constant to get the latter. If you take all possible results of the die roll to be equally likely, then Shannon's formula looks just like the Boltzmann equation. This isn't a coincidence. In fact, Shannon entropy is, in a sense, just a generalization of thermodynamic entropy. The former describes the amount of hidden information in any system. The latter applies specifically to thermodynamic systems. And there's a third, perhaps even more fundamental type of entropy. That's quantum entropy, also known as von Neumann entropy. It describes the hidden information in quantum systems, but more accurately, it's a measure of the entanglement within quantum systems. In fact, the evolution of quantum entanglement may be the ultimate source of entropy, the second law, the limits of information processing, and even the arrow of time. We'll get tangled up in all of that in an upcoming episode of Space-Time.
Hi, this is Jonathan Gardner. I'm going to teach a course on electrodynamics. This is what I learned when I went to college and studied as a physics major. This is real electrodynamics. This isn't hand waving and smiles and happiness and pretending you know when you don't know. The book that we're going to use, and you need to get this even though it costs a lot of money, is Introduction to Electrodynamics. This book is written by David J. Griffiths. It's a great book. This is probably the best physics textbook you're ever going to find in your entire life. This is the second edition. The third edition came out shortly after I graduated. And there's a fourth edition coming out soon. You can find the second edition if you really want it. I don't believe there's too much difference between the different versions, and to be honest, you probably could get by without the textbook. You won't be able to do the problems, of course, which I think is a major part of learning how physics actually works, but you'd be able to learn at least some of the principles and remember them. What do you need to know? Well, if you want to learn electrodynamics, you have to be proficient in the following fields. One is algebra. You know, if you don't know algebra, you're just going to be completely lost. I can't emphasize that enough. You really have to go out there and learn algebra, get used to moving those symbols around. Another is calculus, but you'd be surprised how little you actually need to know to get through everything. So if you just understand the ideas of calculus, what the limit, derivative, and the integrals are, that should be enough. The third thing that you're going to need to know is some classical mechanics. Basically what you would pick up in your first year as a physics student, or that physics class you have to take as an engineer. So this is the F equals ma stuff, you know, 1/2 mv squared, some of the rotational kinematics, and some of the basic principles of how physics works. And the reason why you have to take that is you have to understand you know, what mass and velocity and acceleration really mean, and you kind of have to have a feeling for how physicists approach problems versus mathematicians. And the last thing you're going to have to need is you're going to have an open mind. Some of the ideas you're going to learn are completely different than what you think you already know, which is a good thing. When you learn something new, you hopefully eliminate something you thought was true but isn't. So with all of these things, you should be able to do well in this course. Section 233, Poisson's equation and Laplace's equation. So we know that the electric field is just the gradient, or negative the gradient actually, of the potential, the electric potential. So what happens when we take the divergence of E, or rather the divergence of this gradient? So the divergence of E, well, we already know that's going to be equal to the charge density over epsilon naught at that point. And this is also going to be equal the divergence of the gradient, of negative the gradient. So pull that minus sign out. So we have minus the divergence of the gradient of V. So we have basically minus the Laplacian of V. So we get the result that the Laplacian of the potential is equal to the charge density in space divided by epsilon naught. And this is known as Poisson's equation. All this says basically is that the potential basically accelerates. So it grows ever steeper where there's charge around. And Laplace's equation is just basically what you get if you take a region of space where there is no charge. This is called Laplace's equation. And all this says is the acceleration of the potential there is 0. So if it was increasing, it continues to increase. If it was decreasing, it continues to decrease. And if it was flat, it continues to be flat. So much for that. We're going to explore this more in Chapter 3. The other interesting thing is what happens when you take the curl of E vector. So that's the curl of minus the gradient of V. Well, no surprise there, that's going to be 0. So the curl of any gradient is, of course, 0. So in truth, you know, the fact that the electric field isn't curly gives us the potential in the first place. So this is basically stating what we already assumed to be true. Anyway, hope that really helps you.